Today we're going to examine some of the fundamentals of simple harmonic motion, and we're going to begin by looking at a simple pendulum. A simple pendulum is a point mass attached to the end of a string. I've shown something more than a point mass here. You can see that that ball has some radius, but it's much more pleasing to look at a pendulum like this, so it's close to being a simple pendulum. So I'm going to begin by defining the positive x direction and put a ruler on here. The pendulum's drawn back, and now I'm going to let it go. And you can see that the motion is being traced out there with that curve. It's pretty clear that this is a sine or a cosine curve, and in fact that's exactly what we need for simple harmonic motion. The curve looks a little bit odd, and so we'll put it in a position that's something that's closer to what we're used to. And you can see the equation showing up there, x of t equals a cosine of omega t plus of omega t. And the amplitude is a. And the period is defined as the time it takes for the motion to repeat. So the period is there on the graph. And from your pre-calculus knowledge, you can verify that the period is going to be 2 pi over omega. So what else can we do here? Well, you could imagine a scenario where the pendulum does not begin at the maximum amplitude. For example, you could start it in some other position and give it an initial velocity. And we want to be able to handle a situation like that. And in a situation like that, your curve would be shifted along the x-axis, either to the left or the right. And we can take an example like that. Here you can see that the lower curve is shifted a little bit to the left, and we can handle that by adding delta to the argument of cosine. Now, delta is going to have units of, it's going to have to be an angle because it's inside the argument of cosine. But you can see that the x-axis is measured in units of time. So how do we figure out what delta is? Well, if you manipulate the equation a little bit, pull omega out, then you can see that delta over omega should be the amount that the graph is shifted to the left. And so if you have a graph like this and you want to determine what the equation is, you can do that. All right, so there are other things we can do here. Let's take that equation, x of t equals a cosine omega t plus delta, and let's go ahead and take the derivative. So what's going to happen when we take the derivative? Well, cosine, the derivative of cosine is negative sine, and we're going to have to use the chain rule as well because we have omega t plus delta inside the argument. So when we take the derivative, we get dx dt equals negative a omega sine of omega t plus delta. And we're going to do the same thing again. Take the derivative again. The derivative of sine is cosine, and we're going to have to use the chain rule once again. And so when we do, we get d squared x by dt squared is negative a omega squared cosine of omega t plus delta. Now, take a look at the third equation and the first equation and see if you notice a connection there. You probably noticed that a cosine of omega t plus delta shows up in both of those equations. So now we're just going to make a substitution, and we get d squared x by dt squared is negative omega squared x. Now this is a really important equation because if we have motion that's described by a sine or cosine function, then we'll find that this equation is true. And you can turn that around. If this equation is true of the motion, then we know it can be described by a sine or a cosine function. In other words, we have simple harmonic motion. So if we see this equation, we know we have simple harmonic motion. We often like to find the period when we have simple harmonic motion, and we can do that because we have omega. And so we want to remember these two equations that are boxed here. Now, a few things to consider, a couple of things to note, I should say. Omega squared is going to be greater than 0, so negative omega squared will be less than 0. And the variables here, or the variable x, doesn't have to be x. You could imagine a situation where the motion is vertical, and in that case the variable might be y. You could also imagine some rotational motion that might be simple harmonic, and in that case the variable would be theta. You could also describe motion along an arc, and then you might want to use s. In any event, lots of things can show up as the variable in this equation, and the key is the relationship. If the second derivative is equal to negative omega squared, whatever the variable is, then you have simple harmonic motion. So we're going to end with a simple example of simple harmonic motion, and we'll see some more examples in a later video. So let's suppose that somehow you've determined that for particular motion d squared z by dt squared is equal to negative 5z. Well then, based on the equation we have, we know that omega squared is equal to 5. That means omega is the square root of 5, and period is 2 pi over omega, so that's 2 pi over the square root of 5. Now you might also like to write down the equation for this motion, and so going back to our equation z equals a cosine of omega t plus delta, we can substitute 2 pi over root 5 in for omega. And then the last thing to do would be to substitute for a and delta. But unfortunately, we can't do that given the information that we have. We would need more information to finish this, to finish filling in this equation. So that's it for the basics of simple harmonic motion. And in the next video, we will address the simple harmonic oscillator.